So in this video, I want to talk about things that have confused me as a developer starting out working with graphics and with OpenGL. When starting out, there was a lot of new terminology. There was a lot of very in-depth documentation, and I was finding it very challenging to know where to properly invest my time in a way such that I could learn the things that would help me build the things I want to build instead of just learning some obscure parts of the pipeline. So for that reason, I'm going to provide some gross oversimplifications of how things work, of how the pipeline works, but I do hope to focus on things that I find myself most concerned with in most applications, and that is the programmable parts, the shaders, and how those work, and how your application interacts with shaders, and how they exchange data amongst themselves, and how kind of OpenGL fits into this picture a little bit. So hopefully this is useful to someone out there. So typically an application, a graphics application, would have two parts. One is your application itself. So this is your process. Your operating system gives your process some memory. Then your process loads some resources into that memory, like textures and fonts and things like that. And your application figures out its state, like what needs to be drawn on the screen at this particular moment in time. And hopefully then it has enough information to pass on, to create instructions that will then be passed on to the GPU for rendering. And the GPU is very good at handling those rendering instructions, because a lot of the, kind of by design, a lot of those rendering instructions deal with large sets of floating point numbers. And the GPU is very good at dealing with large sets of floating point numbers, because it has many more cores than a typical CPU. So it's able to run instructions on big multi-dimensional arrays in parallel very well. And a lot of the data that it's working with is sets of floating point numbers. So your textures are 2 or 3 dimensional enormous arrays of floats, where each pixel is a set of 4 floats representing color channels. And your matrices that you use everywhere to transform your points in space are also floating point numbers. Your points themselves are floating point numbers. So the GPU is kind of very well positioned, because of its parallelism, to deal with these kinds of graphical problems that we offload to the GPU. So OpenGL is something that allows for that communication between your application and the GPU. There are different technologies besides OpenGL out there, but talking about OpenGL specifically, it's a client-server architecture where the client is normally your application, so things happening on the CPU, and the server is normally the graphics card. OpenGL is simply a language or an API or a specification that describes how the two must communicate. And the server doesn't necessarily need to be a graphics card. It could be a machine somewhere on the internet. The OpenGL is not really concerned with the implementation of either the client or the server, as long as they kind of conform to the rules that OpenGL kind of puts forth. In a typical application, you create some set of instructions. So your client, your application creates some sort of set of draw instructions, and then sort of chucks them over to the server, which then will run those instructions and draw them on the screen. And this has the benefit of asynchrony, where your application doesn't need to wait for your server to finish drawing. It can kind of continue on its way and respond to user input, for example, or simply just hang out and not waste any cycles until the next frame. So a pipeline is essentially a series of steps that it takes for the stuff that you want to draw to end up on the screen. So if I have an application that wants to draw a series of triangles of different colors, the pipeline describes kind of what would happen to those triangles on their way to finally lighting up pixels on my screen, on my display. Modern pipelines have a way to provide some source code that would affect some flow or some parts of that pipeline. So to kind of inject our own kind of flavor into that pipeline. And these are called shader programs. And shader programs with OpenGL consist of a vertex shader and a fragment shader, and they work together. So these two make up a single shader program. And I'll talk about more in detail about them. But for now, the way that your information goes through this pipeline, just at a very high level, at first your application has some set of points in space, for example, that it wants to draw in some arbitrary space, right? That only makes sense to your application. So you made up your own coordinates for these vertices, and they kind of make sense to you. But the rest of the pipeline has no idea how these should correspond to the screen. So if you define like a cube, it has no idea how far away you are from the cube, how small the cube should be on the screen, from what side are you looking at the cube, and so on. So this is where the vertex shader comes in. And one of its kind of primary responsibilities is to take the positions of these vertices and convert them into a space that makes sense to the rest of the pipeline, so that the rest of the steps can kind of take place and the pipeline can do its thing. And that space that the vertex shader needs to convert your points into is called clip space. And clip space is just basically a cube that's -1 to 1 in each dimension, x, y, and z. Everything kind of outside of that cube will get optimized out by the pipeline. I'll get into that later. So what your application will typically do is define, let's say, a cube as a set of vertices, and this is a vertex array. So it'll pass an array of points to your vertex shader. Your vertex shader then runs once per each vertex and perhaps transforms its coordinates into the clip space. In order to do that, the vertex shader normally needs some kind of a matrix to hint at where the viewer is, where that model is in your world, is located in your world, what kind of projection to use. So if you're using perspective or orthographic projection and things like that, and it can based on the position of the vertex, let's say, and that model view projection matrix, figure out whether that point should be on the screen that is within the clip space. Following that, following transforming these points into clip space, we get into triangle assembly. And this is a part that we don't really have control over, other than we can provide some information via OpenGL about how these vertices make up triangles. So in what order should we be creating triangles out of these vertices and things like that. So triangle assembly is that step. Sorry about that. And then following that is rasterization, which is basically for each triangle we figure out which pixels need to be on. Very simply then the fragment shader runs per each one of these pixels that are on the screen. And the fragment shader's job, its only job, is to set a color for that pixel. That's basically it. I will get into more detail a bit later about some of these parts. So the vertex shader takes in two major kinds of inputs. And these inputs are passed from your application. So one type is a uniform. And uniforms are things that your application sets once and then draws, let's say, a set of vertices. So if your application wants to draw a cube, it's drawing 8 vertices, it'll set a uniform once and then draw all 8 vertices, and that uniform is going to be unchanging for each of these vertices. And the uniform could be your model view projection matrix, or it could be a position of a light, for example, that's unchanging for each vertex, obviously. Or it could be time if your object is kind of rotating over time and you want to use your vertex shader to rotate the object with time. It could be time. The other type of input are attributes, and attributes are different for each vertex. So they're also passed from your application. So if you have 8 vertices, your application might define an array of size 8, where each element is an attribute. And it could be, let's say, if it's a position, it might be each attribute might be a set of 3 floats, x, y, and z. Or if it's some other information like color, it might be a set of 4 things, 4 floats, representing color at that vertex. Or it could be UV coordinates, where each set of 2 points represents the point on the texture where some texture overlaps that vertex, or something like that. So these are attributes, and they're different for each vertex. Uniforms and attributes are kind of prefixes that you can use in GLSL, GL shader language, to kind of annotate your variables in your shader. And these are read-only. Uniforms and attributes are read-only. You cannot set them. They're only passed in from your application to your vertex shader. Varying variables are writable. In fact, you should be writing to them if you're declaring them. And they are a way for you to pass information to your fragment shader. And I'll talk a little more when I talk about fragment shaders about how these varyings are passed in. But note that setting them is optional, or declaring them is entirely optional. And you would just specify the keyword varying before a variable that you define in your vertex shader, and you set it, and it's set per that vertex. I'll explain what that means. However, in the vertex shader, you should set a position in clip space. So this is the GL position, a special reserved variable called GL position, and you set that, and that's important for the next step. So you're taking in some positions in some arbitrary space, and you're hopefully setting a position in clip space, and maybe setting some of these varyings in your vertex shader. The next step is triangle assembly, which basically makes triangles out of your vertices depending on the scheme of your choice, as whatever the API provides. There's different schemes, the triangle strip or fan and things like that. And things that are triangles that are outside of your clip space. Remember that now we're all in clip space after the vertex shader, are going to get optimized out. So we're not wasting time sort of drawing them. As well as things that are facing away. So this is where the actual direction of your triangle is kind of important as well. The next step is rasterization. And this is the step where for each triangle that's being drawn, to oversimplify it, we basically figure out which pixels on the screen need to be drawn, need to be on. A good illustration is here. And it does some other things to figure out if things are overlapping, but just for simplicity, we'll talk about just the pixels being on. And then for each of these pixels, your fragment shader will be run, or your pixel shader will be run. Only for the pixels that are going to be on. And so your fragment shader, just like your vertex shader, is able to take in uniforms, and these are taken. These can be changed once per your draw call, as well as samplers, which are normally contain textures. It's just a way for your fragment shader to read into some block of memory, so it can say like, give me the color of this texture at the coordinate so and so, and it'll get back the color, so it can sample into textures most commonly. In addition to this, your fragment shader can have varyings that are different per fragment. So every pixel will have a different varying assigned to it. And these varyings in the fragment shader are going to be read-only. They are written in the vertex shader, and they are read in the fragment shader. Well, if you looked at the rasterization step, we've got more pixels than we've got vertices, right? How do we set only, in this case, for example, we have red. If you look at this triangle here, it could have set a varying, let's say color, called color, in its vertex shader, and it's set, the top it's set it to red, blue, and yellow. So we've only set 3 varyings. But now in our pixel, in our fragment shader, we've got all of these fragments, and we've got all these different varyings now. Well, the GPU will interpolate between whatever values you set for the vertex between the different vertices, and it'll pass the interpolated value to the fragment shader for that fragment. So for example, this pixel here, this purple pixel, lies between red and blue, and its varying value will then be the color purple. And that's the value that will be passed into it. And so the job of your fragment shader is just to set, normally just to set this special GL frag color variable, and that will determine the final color of the pixel that you'd like to draw on the screen. Let me show an example that demonstrates some of the things that we've talked about, as well as how information can be passed from your vertex shader to your fragment shader. This tool I'm using is called shader.bkcore.com. It's pretty handy. So I kind of recommend it very much for playing around. You're able to switch between vertex and fragment shader up here. So right now we're in the vertex shader. And one of the, remember we talked about attributes and how your application is able to pass arrays of attribute arrays to your vertex shader. And so in this case, the position of the vertices is passed in with the name position as an attribute, and this is different for each vertex. So the job of this method here, this main method, is primarily to take this position in and output it in clip space. So this GL position is going to be in clip space, which, if you remember, is just a space that's between -1 and 1 in each dimension. So the way we go about that is we take our position and we transform it. So we take our vertex's position and we transform it with our model view projection matrix. The model matrix normally describes how a vertex, let's say, makes up a cube, where it's positioned in the world, and how it's oriented in the world. The view matrix describes kind of the viewer and how that vertex appears to the viewer, to the camera. And the projection matrix describes how it's projected onto the camera. So maybe things further away get smaller, so that could be your perspective projection matrix, and things like that. But ultimately, you take this position and you get a position, you should have a position in clip space. And we set the GL position to this clip space position. Now, these model view and projection matrices are uniforms, and these are set once by the application, perhaps at least once per draw call. And I've also defined this new variable called color, and it's of type varying. I'm setting color to the position of my vertex in clip space. But I'm also, remember how clip space is -1 to 1? Well, I'm also modifying it to be between 0 and 1 instead. So -1 to 1 times 0.5 makes it between -0.5 and 0.5. Adding another 0.5 makes it between 0 and 1. So now I have a color where the more to the left something is, the lower something is on the x-axis in clip space, the more black it is. And the more on the right something is, the more red it's going to be. And this is interesting because I'm setting this 8 times. I have only 8 vertices. And I'm setting this, for example, for this vertex once. And I'm setting it for this vertex once. But see how I have a gradient here? That's because of the interpolation that I talked about earlier. So if we look at our fragment shader, there's really not much going on there. Except I've defined, well, these are unused, so I forgot these were in there. But I defined a color varying, just a varying with the same name. And all I'm doing is I'm setting that special GL frag color variable to color. And that's all I'm doing here. And remember that the fragment shader runs once for each of these pixels that make up my triangle. So when the fragment shader is running for this pixel here in the middle somewhere in this gradient zone, its color varying is automatically set to like something between a black and a red, or a very black and a very red color for me by the interpolation. I hope that makes some sense. And please let me know if I need to cover something in a little more detail. And I appreciate you taking the time to have a listen. Thanks.